Okay, I tried to bring in a real-life example for you guys to look at before we look at an example that you can't see atoms. We can't see atoms, we can't count atoms in a traditional way like we would count money or count a number of something that's small enough that we can just go ahead and group them in tens and eventually count them. And this count of beans was between 500 and 600 in your bags that you came up with. All right? I think most of them had between, probably be more accurate, between 540 and 560 beans, somewhere in that effect. And I think most of you were pretty close in your counting, because most of you were in the 500 range. And it was just an activity to kind of get an idea, how can you count something that has a variety of different weights in it? So we took data from somebody's paper, and they figured out that a white bean on average weighed 0.224 grams. The black-eye pea was a little bit smaller in mass, and it weighed 0.208 grams. And the pinto is the bigger of all the beans, and it weighed 0.375 grams. What you were asked to do at that point in time, once you had that information, you were asked to multiply the percent times the weight. When you do that for every one of those, you get 100% of the weight if you add them up at the end. So we want to know the 100% of a weight of one bean in that bag. And that's called the average weight of a bean, based upon our percents, based upon our weights. And that's what you did. And you came up with a number that was a good representation of what we would call the average weight of one bean. Some people would like to take these three, white, black, and pinto, add them up and divide by 3. Why is that not a good way or a correct way of figuring average here? Now, that's the way you figured average in the past, right? Yes?
It's like there's different amounts of each.
There's different percentages of each. If I add them all up and divide by 3, that's saying I have 33.3% of every bean in my sample. I don't have that. I don't have a third of every bean in my sample. I have different percentages because I weighed out different amounts. So when we go ahead and multiply these numbers, we're going to get some values out. .00399. When I use percents, I got to make sure I use the decimal form of that. Most of you know that. That's not going to be a situation where you do it in math, you do it in here, so it won't be any different. Okay?
So you're taking the weight times the percent, right?
Yep, weight times the percent. This second on the first one, I think I did something wrong. So I'm going to get 3 values out when I do this. Now, if you want to write this example down, you can, because it's going to be something similar to another example that we're going to do with an actual isotope. And we need to discuss what isotopes are all about here today. So we're going to take that opportunity to do that once I get these numbers up and we add them all up. Okay? It's up to you if you want to write this down or not. You don't have to. You can just observe this one and write the next one down. All right. So this 0.294 is the average weight per bean.
Is it 294 or 249?
294.
That says 249.
Says 294.
When it's above the bean.
Above the
Lower.
bean.
Lower.
The very
It's in the middle.
No, in the middle of the board.
Oh, sorry. Okay? So 0.294 grams per bean. Then what you did was you weighed out the total number of beans that you had. Okay? So they weighed out 153.76 grams that they had of beans. And grams go down here and beans go up there. And so what you did the same thing. You put the weight per bean down here. So you put the 0.294 grams per one bean, right? And you multiplied that out, and you got the actual number of beans that you would have in that sample. If the weight goes up, you have more beans. If the weight goes down, you have less beans. That's pretty easy to understand that concept. You know that. So 523 beans. So you counted beans kind of in an indirect way. You found the average weight per bean, and then you went ahead and took the weight of everything, and you came up with a number, 523. And I think most of them have between 540 and 550. And we're dealing with something that doesn't have exact weights, all of them. They don't all have exact weights. So we're not going to be perfect in our number or count, because each bag has beans and they all have a little bit different size and shape and that when you deal with them. But we got pretty close. Now, is there a bean in the bag that would have a weight of 0.294 grams? No. Is there any beans that would have that weight? Possibly could. How often are you going to find it? Probably in that bag, maybe not at all. Any questions? So that's an example that we're going to look off of and build off of in which to do an actual example of finding an average weight. So that's what we're going to do next, is we're going to find average weight of an atom. Okay, average weight of an atom. So how do you do that? So it's real similar. Okay, I need to give you a little history here first before we get to this point where we do a problem. And this history is that they developed an instrument that they could divide off all of the isotopes in a sample. It's called a mass spectrometer. Okay, a mass spec. And they still use it for molecules of all different sizes, for compounds of all different sizes. And this probably went through a lot of different developing stages and how good of an instrument it is. But I'll kind of give you an idea what it will look like. So let's say that we have copper gas. and the copper gas is sent through an ionizer. And what that does is it charges it with a positive charge. Okay? Then it's sent through an ion accelerator, which means it basically just pushes those atoms and accelerates those atoms so that they're moving along at a fair amount of speed. I'm sure that can be adjusted to whatever speed that they would want. Slow or fast, however they want to do it. Okay, this would be a magnet, that magnetic property that would be north and south. So these are magnets. Kind of like what other experiment? Remember what other experiment we had the magnets?
Cathode ray tube.
Cathode ray tube. Really similar to that concept, that idea. But these are protons, not electrons, or positive charged ions, not electrons going through. And they find out when it goes through, it divides off into two different types of particles. And they hit at two different spots. Why do they hit at two different spots? Because they have two different weights. Which atom do you think has the bigger weight? A or B? So I'm going to have you guys raise your hand. How many think A has the bigger weight? Raise your hand. How many think B has the bigger weight? Wow, you guys are good. Okay, what law are you using to know that B has a bigger weight? No? Newton's law of motion. Every object in motion stays in motion. Object at rest stays at rest. So the bigger the particle, it will want to continue to go in a straight line, and there'd have to be a bigger force that will deflect that particle. And so the B takes a little bit longer for it to be deflected because it has a bigger mass and it wants to continue in a straight line. Where A is lighter and it'll be easier to move its motion. That's everyday life. When you see things that happen, move along, a big mass is going to be hard to change its direction, where if it's a small mass, it's going to be a lot easier, okay, with less force. Any questions with that? So they were able to say, okay, A is a certain type of atom and B is a different type of atom for copper. And they were able to, if you look on the page that you are on, they were able to identify those as two different isotopes. Those two different isotopes, what are they labeled? Copper, what, dash? Am I on the right page? Top left? 63. All right. Who's 63 in football number? Anybody? No? Okay. Copper, what's the other one? Copper, 65. Anybody 65?
I think that's your six.
Huh? What does that 63 and 65 mean? They identify the isotope and identify something about the isotope that's different. What do we know about copper that has to be the same in both of these copper atoms? It can't change. They have to have the same amount. What's that?
29 protons.
They have to have 29 protons. So each one of these up here of copper has to have protons that would be 20, did you say 5?
What are they? 9.
29? Okay? And so it's just the atomic number. That's all you look at for number of protons anytime you want to look. Now neutrons makes the different weights. Remember we talked about Dalton's atomic theory and says all atoms of the same element are exactly alike, and that is wrong. Mass spectrometer says no, there's two different atoms for copper. There are ones that have 29 protons each, but the neutrons differ. Anybody want to take a guess how many neutrons that copper 63 has?
A lot. It's 13. 34.
63.
No, 63, that's a good guess because you think, well, that should identify it. But the mass number, and we'll find this out later, and build upon this, is the number of neutrons and protons. So now with that information given to you, 34.
Do we need a copy of this down?
If you want to, you can. It would help maybe to go back and know the difference between isotopes and that. But this is part of it. Okay? And then copper 65 would be what? 36.
Wait, how do we get that?
We subtract out the protons from the mass number. The mass number is total protons and neutrons added together. Protons, neutrons added together gives you the mass number. Now, it's not the atomic weight. It is the mass number. It identifies the atom. Biologists like isotopes written this way. Okay? I like isotopes written this way because I don't have to look at the periodic table. And isotopes written this way is what I like. The biologists don't like this way. Well, first of all, you have to know what the symbols stand for. And if you don't know it, then you have to look it up on the periodic table. Chemists, or knowing chemistry, you know that's copper. Cu is copper. Also, copper 63 doesn't tell you anything other than looking at the periodic table. You have to find the number of protons, look at the atomic number. This tells you the number of protons. It's the number down below. You don't have to look at the periodic table. I know that that number is the number of protons. I know the top number is both neutrons and protons, and I can subtract the two to find out the number of neutrons. Okay? We'll go over both of these methods and use both of those in which to write out information about those particular atoms later on. It's just a kind of review or preview of what we're going to do. All right. So why do we bring up these two isotopes? Why are we working with these? What's the reason? We want to be able to understand how they come up with that average for copper. The average for copper is 63.546. So if you look at the periodic table, any periodic table, it tells you the average weight of copper or any of these elements, and it's 63.546 for copper. We want to know how they came up and calculated that. That is the answer. We need to figure out how they calculated it. I bet you guys could tell me how they calculated. So we're going to do this. We're going to put copper 63 up here. You already have it on your paper. I'm just cleaning it up for me. And what I'm going to do is I'm going to put a percentage here. So what's the percent of copper 63 found in any sample? 69.15% of the time. That should look familiar to our examples that we had with our bag of beans. Okay? I gave that to you. The other one, there's only two types of copper isotopes. The other one is what? 30.85%. So about out of 100, about 30 or 31 is be copper 65. And about 70% would be copper 63. So this copper penny that's before 82 has about a 70 to 30% ratio. If I would look in here, I would see about a 70 to 30% ratio of those atoms in that copper penny. So guess what I have to do to find the average? I'm going to have to multiply by what? The mass. And they give this mass as like, it's kind of a different way. It's not grams, it's like AMU. So I'm not going to really focus upon AMU other than to tell you that AMU is a relative weight. And what I mean by relative weight, since we don't want to use numbers that are really, really tiny for weights, which we would have to, what we'll do is we'll say, you know, we're going to make a standard weight. And that standard weight is going to be carbon. And it's going to be carbon-12 isotopes. So when you look in your book at carbon-12, what is the weight in AMUs for carbon-12?
12.
Exactly 12. So it's like a meter 6, exactly a meter. You know, there's no significant figures there. It's exactly 12. And so guess what they do is they relate everything to that carbon-12 atom, and every weight is relative to that 12. So they're saying that copper 63 relative to the carbon atom has a weight that is really, really close to a whole number, but it's not exactly what that is. And that number is 62.9296. And that's in AMUs. Right? I'm not going to put AMU, but that just means it's not grams right yet, but it's AMUs. And then the next one they say is 64.9278, we'll say, around it. So guess what we do with those numbers? You guys know, right? We multiply them out, times the percent, we add them up. So I didn't leave myself room, but I'll put the answer down below. We add them up, and we should come up with an answer of 63.546. Just exactly the way it is on the periodic table. Okay? So you go ahead and do that and see what you come up with. You do the same, and I'll do the same, and we'll see what we come up with. And we're really close. So your answer is always on the periodic table. Anytime you do one of these problems, I give you a problem in a test or a quiz. The nice thing about it, you know the answer. But don't just write the answer because you're not going to get credit for it. You just write the answer. Okay? I give you credit for knowing that that should be the answer, but you have to show the work to get there. Okay? Any questions about that? So what they did is they said, okay, those are AMUs. We need to come up with a way in which to measure something in the lab that we can actually measure, because we can't measure just an atom. We can't even measure a trillion atoms. It doesn't even register on a balance. A trillion atoms wouldn't even register on a balance. So we've got to come up with a way in which to be able to weigh things out and count atoms. So Avogadro came up with this way, and I'm not sure, we're not going to go through all the specifics on how it came up to be this way, but he found out, Avogadro's number, is that if we have one unit, it's called a mole. Now how they came up with moles, M-O-L-E, I don't know. But 1 mole of anything, and we'll say in this case atoms, is always equal to Avogadro's number, which is 6.022 times 10 to the 23. That means that if you take that number of atoms and put them all together, you're going to have 1 mole of atoms. It's like 1 dozen is equal to 12. 1 gross is equal to 144. Years, what's a decade? 10 years. Century.
100.
Okay. All right. So what we can do is we can relate a count of mole atoms to a big number of atoms it would take to weigh something out. Any questions with it? This is a count. Don't ever. This is just a way to express a really big count when we don't want to express it as in scientific notation. Okay? So then how does that relate to the average atomic weight? Because that's what we've been talking about, and then all of a sudden I come up with this idea about counting atoms, and a mole of atoms equal to Avogadro's number, which is 6.022 times 10 to the 23rd. Well, 1 mole of atoms, when we count it out, guess what we always come up with? For every particular element on the periodic table, we come up with the average weight, the atomic weight. So if I have 1 mole of carbon atoms, that's going to equal 6.022 times 10 to the 23rd atoms in total, but it's also going to equal the weight of carbon in grams. And it's going to equal a weight of 12.0, and then as you go on and look at carbon, it's 12.011. Yours might take it out a little bit further. So we did our thing with our the beans, and we said an average weight of a bean was like 0.29 something, and then that allowed us to figure out the count. All right, so let me give you another one. You guys tell me what you think it's going to be. So 1 mole of scandium atoms. How much would it weigh? Find scandium. What's the weight of scandium? Element 21. 44.996.
Yeah.
Okay. All right, I'm going to give you a tough one here. I'm going to change things up a little bit. I'm going to go do this way. How much does that weigh? 6.022 times 10 to the 23rd atoms of calcium. You guys are good. Okay? 40.078. Because you knew that 1 mole is equal to this number, and you can make that conversion in your head and know, well, they're the same. Right? So, one more. Let me do this here. I'm going to give you a weight. And then you need to tell me how many moles that would be. Okay? So I'm going to go 65.409. It's supposed to be a 9. Grams of zinc. How many moles of zinc atoms would that be? How many? 1. How many total atoms would that be? So how many total atoms? 6.022 times 10 to the 23rd. What do we, when we use these, how do you think we're going to use them based upon what we did in Chapter 2? What does these allow you to do that we use Chapter 2 to get ready for? What if I wanted to had so many moles of scandium atoms and I wanted to find how many grams I'd have? I'd have to do what? Yeah, and what do we call that process of canceling units out? We call that conversion. You guys get to do more conversion, okay? So we're going to do a couple conversions really quick, right? It won't take very much time at all. So I'm going to pick 100 grams of carbon atoms. Okay, and I want to know how many moles of carbon atoms I have. Okay, does anybody want to help me? So what do you think needs to go out in front of my conversion? 100 grams of carbon. What unit should go down below? Grams of carbon, just like we did when we did converting. What goes above?
Avogadro's
What's that?
Avogadro's number?
Well, it would be if I wanted to know total number of atoms, but I want to know moles of carbon atoms. So, unit of mole goes up above here. So what number goes down here for carbon? 12.011. Jared, what question do you have?
Nothing, I figured.
Okay. And what number goes up here? 1. Look at that. Now we know the count of carbon atoms in moles. So we go ahead and do our conversion and we get our answer. We get 8 well, we'd have 4 digits, so we want to keep consistent on significant digits, keep using them, talking them from time to time. 8.326. Got it. Okay, let me switch things up. I want you to try to do this. Units never lie. You cancel them out, you get your answers. They're never going to be messed up on you. So now I'm going to give you a different way of looking at this. Let's go, and we have 0.395 moles of aluminum atoms. And I want to know how many grams that would be of aluminum. Go ahead and set that up and see if you can solve for that. This is really easy. Easy stuff. You guys done conversions, you know how to do this. This is so easy. We'll do one more after this, and then I'll have an 8-problem assignment. They're just all one-step setups to cancel out your units and get to units that you're asked about. I'm making sure to label everything too. There's a tendency for some of you not to label, and it gets you into trouble.
Okay, so what's the label for
MOL?
moles?
Yeah, they take the E off. I don't know. It's just MOL. I get tired of writing the E. So what goes with moles? 1, and this is what, 20? 9, 8. You got your answer. Pretty easy stuff. Got one left to do. What'd you get for an answer for that anyway? 10.7, right?
Yeah.
Okay, last one. Okay, last one and we'll do. We got to get atoms in here. We need to use that scientific notation. So I'm going to go ahead and give you probably the toughest one you'd have to do. And so we're going to say 15 grams of, we'll do, let me see who I'm partial to. Let's go with silver. And let's see how many total atoms that would be. Not moles of atoms, but total atoms of silver. So instead of 1 mole, what will we use? Avogadro's number. Avogadro's number you have to use in this one. Because I'm not asking moles of, now if I had moles of atoms, that would be a lot easier. You just put 1 in there. And now I'm asking for total number of atoms. And so you need to use that one. Set up your conversion setup. Cancel out your unit to get to the unit you want to solve for. And then see if you can calculate it correctly with your calculator. Is that what you got? To the 22nd?
Okay.
6.022. Well, I just put in 6.02, so you might have got a little bit number because I'm so used to using it as 6.02 and not going out to 6.022. But it might be the same.
Do you want us to use this Avogadro's number out of the book? Or?
No, You can use 6.02 if you want to. If you want to go 6.022, that'd be fine. I'm not a big deal. Yes, Tabby?
What's the answer times 10 to the what?
Times 10 to the 22nd is what you should come up with on your calculator.
How do we know how many digits out we're supposed to do?
It's a good question. There's 3 here, and I'm going to put 3 in my answer.
Oh.
So anytime they give me a measurement... Okay, so your assignment to do is... there's tons of problems to do in the back of the book. The Appendix D. So if you turn the back of the book, there's a purple section. And the page we're going to be focus on is page 886. And I'm going to have you do problems 95 through 98, A and B. Please have them done. It's a completion grade. If you don't have it done, then we're going to go through these answers and you have an alternative assignment you'll have to do if you want credit for it.
Are we handing these in them?
No, we are not handing these in, so you can put them in your notes. But I will come around and check to see if they're done. So page 886, 95 through 98, A and B. All right, you guys did a nice job of figuring out those, going through those. Thank you.